All right, ladies and gentlemen, so what we've been working on up until in the last couple units has been a binomial distribution. If there's a set number of trials, how many times will we be successful? And we're going to look at something a little different today. We're going to look at a geometric probability. And I had mentioned it that earlier, but basically a geometric probability is where you keep going until you get a success. And actually, we did a problem kind of like this earlier in the year when we did our simulation on having a boy. And that'll come up here in a second, and I can show you where that math comes from. But remember, they kept having kids until they had a boy. That's a geometric probability setting. And so there are conditions, just like for a binomial, that we have to hit. So instead of bins, we get bits. Is it binary? Is each time independent? Is the chance of success the same? But then the trials is, are we going to keep going until we find a success? So now the n is no longer fixed. So one of the house rules in Monopoly is if you roll doubles while you're in jail, you can get out of jail. And the question is, how long would it take you to get out of jail on average? If you just kept rolling until you got out of jail, how long would it take? So is this we're going to call it a random variable. We're going to define y as the number of attempts it takes to roll doubles one time. So is it a geometric setting? Well, the answer is yes, it is. It's binary. It's independent. The chance of success each time is 1/6, and we're going to keep going until we get out of jail. So this is a geometric setting. And what you'll see is geometric probabilities or geometric distributions will generally have a shape kind of like this. This is a setting we'll talk about tomorrow in class, but that's what a geometric distribution looks like. It is definitely not symmetric. It is almost always going to be, right skewed, because you could do it on your first try, woohoo, get super lucky, but there's a chance that this could go on forever. You could be super unlucky and have to roll doubles, multiple times. So that's what we're going to talk about here about the probabilities. So we can find the probability of each one of these, but we always, before we start using the formulas we're about to learn, you have to make sure that you've met the criteria, or else we cannot use the formulas that you're about to see. So what are those formulas? Well, the probability of any one occurrence is given by this formula here. Now here's where it gets a little and this formula generally will appear on the multiple choice, but not the FRQ section of the exam. I'll double check that and make sure that that's true tomorrow in class. But regardless, we want to write this down. So we got, what's your probability of it taking this many tries? This is the probability of success. K to the n minus 1 times the probability of not successful times the probability of successful. So let's look at one of these. And this is, I've got my answers hidden down here. Excuse me, let me fix that. So find the probability that it takes 3 turns to roll doubles. So we want to find the probability that y equals 3. Now remember, the probability to roll doubles is 1/6. That's if you roll 2 dice, chances of rolling double are 1 out of 6. We learned that earlier. So my probability is going to be 1 minus 1/6 to the 3 minus 1 times 1/6. Or 5/6 squared to the 1/6 times 1/6. And if you, so that would be how you would find A. And if you do that in your calculator, you get the probability that y equals 3 is 0.1157. Now, to do the probability that it takes more than 3 turns, what we'd need to do is we would additionally need to find, and we're just going to go down here and cheat and show you the answers. You would have to find the probability of 1 minus the probability of 3, 2, and 1. And this one's kind of complicated, and I'm going to show you how to do that one in your calculator tomorrow. So we'll talk about how you do that one tomorrow in class, but there's the answer for that problem. But once again, for A, they get the exact same answer we did. One of the cool things about this is the expected value of y, or the average value of y. If we did this over and over again, on average, the amount of time it would take is just 1 over p. Well, in our example, that was 1/6, so 1 out over 1/6 is going to be 6. So on average, it would take 6 tries to roll doubles. There's going to be variation there, and we're not going to get into how to calculate the standard deviation for that. That's beyond the scope of this class. But if you remember, we did all those simulations on the one-child experiment earlier in the year, and so the expected value for the one child, for the one boy experiment, well, the probability of getting a boy was 1/2. So the average number of children in each household is going to be 2. So that's it. Now we've covered everything in Chapter 6. This is just all the stuff in the last section we covered. This going to know all our stuff about the binomials. Geometric's a little piece of this. Binomials are incredibly important. We got to have the binomials down pat. And so I will see everybody next class.